All right, good afternoon and welcome to the final session of our physics crash course. My name is Dane Campbell and we have Miss Rose. All right, so first we'll do a recap of the topic of resistance. Miss Rose.
Good afternoon, everyone. So we are going to begin by looking at a question that's based on the topic of resistance. This question is coming from the May-June 2012 paper 3, and it's question 2. So there is a group of fifth form students that was given a school-based assessment to investigate the relationship between voltage and current for a resistor at constant temperature. You are first, they were also asked to draw a voltage current graph and therefore indicate or calculate the resistance of the resistor. So figure 1 shows a circuit diagram of the apparatus that was used to do the investigation. And here we have the different components, and we have some labeled parts A to E. So the first task is to write the name of each of the components that's represented by the letters A to E as shown in the figure. Now it's important to note that you realize B and C, they look pretty much the same apart from the fact that they have different letters. So it means that we need to bear in mind that one of them is connected in series with the component R, while the other is connected in parallel. So remember that ammeters are connected in series with the components and voltmeters are connected in parallel. So we can bear that in mind when labeling. So if we start off with A, realize that we have two positive and negative terminals connected end to end. So that's a battery. You have one positive, then one negative, and then another positive and another negative. So we have a battery for A. B, which is connected in series with R, we would say that that is the ammeter, which is going to be used to measure the current that is flowing through the resistor. And then C, which is connected in parallel, is the voltmeter, which is going to measure the potential difference across the resistor R. All right, moving on to D, we have a variable resistor or a rheostat, which is used to alter the resistance in the circuit so that you can get varying current and voltage readings. And finally, E is an open switch. All right. So having set up the circuit, the students went and got some results, and the results are recorded in table 3. So they got results for current and voltage. And here we have six pairs of readings. Of course, you're asked to use the results that were obtained by the students, plot a graph voltage against current. Right? So it would be voltage on the y-axis and current on the x-axis. So you're also told to begin both axes at 0, which is the origin, and that's for 6 marks. So the graph has been pre-drawn. You notice that we have our title, graph of voltage against current for a resistor at constant temperature. The axes are labeled. Y-axis is, and the x-axis is the current. And notice that when we label our axes, we use the symbol for the quantity and the symbol for the unit, right? So you should be familiar with plotting of points. So I don't think we need to go over that. So we have our 6 pairs and we draw our best fit line. Right. So having the next task is to calculate the gradient of the line. And we know that to calculate the gradient, we use the formula y2 minus y1 divided by x2 minus x1. And always be sure to indicate the points that you use for the gradient on the line itself, and then you substitute those values into the formula and would end up getting a value of somewhere around 3 volts per ampere. Always remember the unit for the gradient as well. Only time there is no unit is if the units will cancel each other. So it's volts per ampere for the unit, and the okay, so we're going back to the graph. So note that we have our x2 and y2 values, 0.59 amperes and 1.80 volts respectively, and our x1 and y1 values, 0.10 amperes and 0.30 volts respectively. You notice they are labeled on the graph, and you try to use a large triangle so that you can be sure that the graph is measuring the change throughout the entire set of results. All right. So having calculated the gradient, we obtained a value of 3 volts per ampere. Remember, volts on the y-axis and amperes on the x-axis. So you would also divide the volt by the ampere in getting the unit for the gradient. So that's why we end up with volts per ampere. Right. Then finally, well, not finally for this graph, you're asked to use the gradient to determine the resistance R of the conductor. Now remember that if we plot voltage or potential difference against current, then the gradient based on Ohm's law should be the resistance, because resistance is equal to voltage divided by current. And that's the same thing that you have on the graph, voltage over current or divided by current. So the same value that you get for the gradient would be equivalent to the resistance. The volts per ampere is the same as ohm. So the gradient is equal to the resistance, which is 3 ohms. Okay. Now, if the present resistor is replaced by another resistor and the circuit is closed, the voltage is now recorded as 1.9 volts and the current as 0.48 amperes. You're now asked to calculate the resistance of this new resistor. So we have our voltage and we have our current. So we can use Ohm's law to calculate the resistance. Resistance is equal to the voltage divided by the current. So we would divide 1.9 volts by 0.48 amps, and that would give us a value of approximately 4 ohms. It would be 3.9 something. We can round up to two significant figures, and that would be 4, 4 ohms. All right.
All right, so we'll start the content for session 4. And today we'll be looking at particles in the atom, radioactive emissions, half-life, and of course, we look at some past paper questions that are related to these topics. All right, so particles in the atom. Now, we're going to be talking about the different particles that are present in the atom. We know that we have protons, neutrons, and electrons. Protons are positively charged, and they are in the nucleus alongside the neutrons, which are uncharged. The electrons, however, are negatively charged, and they move around the nucleus in orbits or shells. So protons and neutrons are inside the nucleus, whereas the electrons are outside and they are in shells. Now, in terms of charge on the proton and the charge on the electron are equal in magnitude, which is about 1.6 times 10 to the minus 19 coulombs. But those charges are opposite in sign. So for the proton, we mentioned they are positively charged, but the electrons are negatively charged. So the only difference is the sign of the charges. They have the same value, which is the actual value is 1.6 times 10 to the minus 19 coulombs. Now, protons and neutrons have similar masses, but they are far more massive than the electron. So further down, we look at the relative masses, and we'll see that the proton and neutron are very heavy compared to the electron. All right, you should also know that atoms are generally neutral, and this is because they contain an equal number of protons and electrons. All right, protons and electrons are of opposite charges in terms of sign, but because they have the same magnitude, then equal numbers will result in a cancellation of the charges. So the atom will have a net charge of 0. In terms of nuclear stability, we can look at the neutron to proton ratio to tell if the nucleus of an atom is stable. Now, if the neutron to proton ratio is suggesting that you have too many neutrons or too little neutrons, then the atomic nuclei would be unstable. All right. So the unstable status of the nucleus would be due to either too many neutrons or too few neutrons. Now the mass number is represented by A, and you'll need to use this relationship A equals Z plus N when you are figuring out, for example, how many neutrons are in a nucleus or how many protons, depending on what information you're given. So we use A for mass number, which is the number of protons plus the number of neutrons. And this is also referred to as a nucleon number, because the proton and the neutron are called nucleons. The atomic number is represented by Z, and this is the number of protons in an atom. And it is also called the proton number, which is, making it obvious. The neutron number is the number of neutrons in an atom, and this is represented by N. So what we have is that if you add the proton number and the neutron number, you'll get the mass number. So A is equal to Z plus N. Isotopes, that's another topic that you should look at. Now, isotopes are, the word isotopes refer to atoms of an element which have the same number of protons but different number of neutrons. In other words, they have the same atomic number but different mass number. So they belong to the same element. The periodic table is a diagram or a figure which arranges the elements in order of increasing atomic number. Generally, that is the case. And all the elements in a row, which we call a period, have the same number of shells being filled or filled with electrons. And when you go across the period, the number of protons increases by 1 for each successive atom each successive element you go to from the previous one. So when we look at the diagram of the periodic table, which you should be familiar somewhat with, you will see that the number of protons, that is the atomic number, increases by 1 each time you move further to the right. All right, so this table we look at here will summarize the mass and charge of the 3 subatomic particles. We have the relative mass in column 2, and we see that the proton and neutron are very similar in masses. The neutron is slightly heavier than the proton. So this is the relative mass, meaning that when you compare them to each other, the proton is 1836 times the mass of the electron, while the neutron is 1839 times the mass of the electron. In atomic mass unit, we have the mass of the proton being 1, the neutron being 1 as well. They're roughly the same. But the electron now would be 5 over 10,000, right? In terms of its comparable mass to the proton and neutron. So the electron is very, very light compared to the other 2 particles. Now in kilograms, we'll see if we use 3 significant figures, we'll see that the mass of the proton and neutron are not different. We'd have to go further. This would have to be more precise to actually see the difference in mass in terms of kilograms. So the proton and neutron, you know, they are very close in terms of their masses. But the electron now is very light. This is 10 to the minus 31. All right, so that's by a factor of 10,000. All right, times. All right, now the relative charge. We have +1 for the proton, 0 for the neutron. The neutron does not carry an electric charge, and the -1 for the electron. So the proton and the electron have the same magnitude, which we mentioned before, same magnitude of charge, but opposite signs. The last column here shows the actual charge in coulombs. However, I'd advise you to recall the relative charge and the relative mass, because normally they would give you the actual masses. If you are to use these values, to work out a question, you'll be given these values, if anything. All right, so what you should try to remember are the relative masses and the relative charges. Okay, so representation of an atom, where we have a nucleus in the center containing protons indicated by red circles here with a positive sign, and the neutrons by a blue circle. So this is the nucleus, and then we have the electrons in the shell. This is helium atom. It has 4 nucleons, so 2 protons and 2 neutrons, and 2 electrons. So if we consider the charge of the helium atom, we will see that it is 0. So 2 positive cancels 2 negative. All right. So the charge on the atom is normally 0. All right, this is a representation of a nuclide of carbon-14. We just want to emphasize the equation that we mentioned before, A equals Z plus N, and how to represent a nuclide. We have the mass number at the top on the left and the atomic number at the bottom on the left. Then the symbol of the element. All right. No, we don't normally put the neutron number, just the mass number and the atomic number. So this is for carbon-14. All right. So this is a specific isotope of carbon. All right, we are going to go to a simulation for the atom, just to emphasize the nature of the periodic table and how the elements are classified. Okay, so this simulation is called Build an Atom. And what we can do is to try building our own atoms by adding protons, neutrons, and electrons. Now, this drop-down allows us to see the charge, the net charge on the atom, whether it is neutral, negatively charged, or positively charged. This drop-down allows us to see the mass number. Currently, it's at 0 because we don't have anything inside here. Now, the X represents where the nucleus would be, while the broken circles represent the electron shells. So we can show the element. We can show whether it is neutral or it is an ion. And we can show whether it's stable or unstable. We're going to leave the stability part out for the time being. Now, over the right-hand side at the top here, we have the periodic table with some of the elements. So hydrogen is really the first element. If we have 1 proton in the atom, then that's hydrogen. All right. Now, however, what we can see here is that it's an ion, because the proton is positively charged, there are no electrons, so we have a positive ion. So this would be the hydrogen ion, all right? To make this into an atom, we would need to add an electron. Now, the electron has to go to a specific area, and if we try to put it in the second shell, it will not go. It will go in the first shell, all right? Because it has to start at the lowest energy level. So now notice we have a neutral atom, right? So one proton, one electron, the charges cancel each other because they are opposite in sign, but equal in magnitude. So they cancel out each other, leaving you with a neutral particle. So here we have net charge is 0, mass number is 1. The electron does not contribute to the mass of the atom. As I said, it is very light, so it doesn't count as in the mass, just the proton. Now, regular hydrogen does not have any neutrons, just one proton, but we can add a neutron. Adding a neutron doesn't change the element, still hydrogen. And in fact, this type of hydrogen is called deuterium. All right. So this is an isotope of hydrogen. Notice mass number is 2. If we remove the neutron, mass number is 1. So this is regular hydrogen. But with the neutron, it becomes deuterium, which is an isotope of hydrogen. This is, let's check the stability. We have one proton, one neutron. It's stable, right? So 1-to-1, there's a 1-to-1 ratio here. This would be a stable nucleus. However, if we put 2 neutrons, then the atom, the nucleus becomes unstable. All right, because we have too many neutrons now for the one proton. All right, so this isotope of hydrogen is unstable. Notice the mass number is 3 because we have 3 particles, and each of them is considered to have a relative mass of 1. All right, so this will be unstable because you have 2 neutrons and only 1 proton. All right, so that's how the stability works. Now, just to show that the proton number determines the type of element, if we add 1 more proton, we no longer have hydrogen, we have helium. All right, this will be an ion, so we need 2 electrons to balance, so it becomes neutral. If we add 1 neutron, it will be stable. All right. Let's see, if we add 1 more, it becomes unstable. But if we add a proton, we change the element and it becomes lithium. So each time you go across the periodic table in a row, right? If you move from lithium to beryllium, you increase the number of protons by 1. So if we increase by 1, we're going to get beryllium. All right. But we have to add a neutron or 2 to make it stable. But pay attention to the protons. The proton number is what determines the element. If we add a proton, we're going to get a different element. This time we have boron. And if we have 6 protons, we're going to get carbon. All right. So that is how the periodic table is arranged in terms of increasing proton number going across the period. And then the shells will be increasing going down the group. All right. All right, so that's for the simulation. All right, so we have the periodic table. This is one particular example. You have different ways in which they represent the periodic table, but the elements are placed in the same order. So we have hydrogen with an atomic number of 1, the first element. We have helium with an atomic number of 2, followed by lithium 3, and so on. So as you go across, you will see increase in numbers, just like in the number system, increasing by 1. That is the atomic number. All right. So if you know the atomic number, you can really know the element. All right, so we'll go to a question now. Ms. Rose will take over here.
All right, so this question is from the January 2009 paper, and it's question 5, and we'll be looking at parts A to C. So firstly, you're asked to explain the meaning of each of the following terms. First is the atomic number, and as was just explained earlier, the atomic number is also known as the proton number, and it tells the number of protons that is in the nucleus of an atom. The mass number, which is also known as the nucleon number, gives the sum of the number of protons plus the number of neutrons that are present in the nucleus. Thirdly, we are asked to define or to explain what the neutron number is, and the neutron number is simply the number of neutrons that are present or that is present in the nucleus of an atom. Right? Now, part B says with reference to the symbol, and the symbol is X, representing the element, A at the top left and Z at the bottom left. You're asked to write the formula that links the neutron number to the atomic number and the mass number. Now remember that the A represents the mass number, Z represents the atomic number. So because the atomic number tells the number of protons and the mass number tells the number of protons plus the number of neutrons, then we can write that the mass number, which is A, is equal to the atomic number Z plus the neutron number N. Right? Of course, if you wrote any variation of that, if you have Z equals N minus A, then that would work as well. But generally, we use the equation in this form: A is equal to Z plus N. Right. You're asked then to describe the relationship between the shell model of the atom and the periodic table. So remember, we just discussed earlier that the periodic table basically classifies the elements in increasing atomic or proton numbers. So as you move to the right of the periodic table, then each successive element has one additional proton. And remember that The electrons now are given or they're present in electron shells. And because in an atom, the number of protons is equal to the number of electrons, then as you move to the right of the periodic table, you increase in proton number as well as the number of electrons that are being put in each of the shells. Right? So each successive element in the period has one more electron and one more proton. Next question asks to explain the meaning of the term isotope. You can recall, or you should, or you may know that the prefix iso means same. So an isotope or isotopes are basically atoms that are from the same element and they have the same number of protons. However, there is a different number of neutrons. So as a result of that, the atomic number will be the same, which is the bottom number, but the mass number, the nuclear number, which is the top number, will be different. Right? So for instance, you can refer to Mr. Campbell had talked about hydrogen. There are three main isotopes of hydrogen. You have H1, H2, and H3. So all of those would be isotopes of hydrogen. Another example is carbon 12 and carbon 14. Carbon 12 has 6 neutrons and 6 protons, whereas carbon 14 has 8 neutrons and 6 protons. So you realize it's the same element. The bottom number, the proton number would be the same, but the mass number is different because there are different numbers of neutrons. Okay. Right. So we have another question. This is from January 2014, question 6, and we're doing parts B to D. Explain why an atom is normally neutral and stable. Now, you will recall we mentioned that the number of protons and the number of electrons in an atom is the same. So because protons are positively charged and electrons are negatively charged, if there are the same number of protons as electrons, then the charges will cancel each other out. So an atom will be electrically neutral. Now, in everyday life, then we would expect that atoms or particles in general, they tend towards stability. And that is why the more common elements or the common forms of the elements tend to be stable. So we look at the neutron to proton ratio. If there are too little or too many neutrons, as was mentioned earlier, the atom becomes unstable. So the heavier elements like uranium and lead, some of those, because the neutron to proton ratio it gets larger, then the atoms become less stable. But mostly in the lighter atoms, the ratio of neutrons to protons is pretty small. It's usually almost a 1-to-1 ratio, and that makes the atom more stable. Now, figure 5 shows the structure of an atom of an element X. You're asked to state the mass number, the charge on the nucleus of the atom. So if you look at the diagram, there are 6 neutrons, and we can see there are also 5 to match with the 5 protons. So remember that the mass number tells the sum of the particles, the subatomic particles that are present in the nucleus, which would be the protons and the neutrons. So if there are 5 protons and add 5 plus 6, and that would give us 11. So the mass number of the atom would be 11. Now the atomic number is the same as the proton number, and it's there right there for us to see there are 5 protons, so the atomic number is 5. Now as it relates to the charge on the nucleus, the nucleus only is concerned in a sense with the neutrons. So remember that the neutrons do not have any charge. So the charge on the nucleus would be the charge that is due to the protons. So the relative charge of the proton, as we said, is +1, and there are 5 protons. So that would make the charge on the nucleus +5. And you're asked to write the symbol for another possible isotope of X. Now, generally you could write almost any combination of mass and atomic mass number, as long as the atomic number remains at 5, then you could have, say, a mass number of maybe 10 or 12, somewhere along there. So you would just write the symbol, write back X for the chemical symbol, ensure that the is the same, and you have 10 here. Of course, you could use another number. So you could use maybe 12, maybe 13 or 9. Of course, not too far out, because remember that we want it to be something that could possibly exist in nature. Want the proton neutron to be or too far outside of a. So we have 10 for the mass and atomic numbers respectively. All right, so we move on to hand over to Mr. Campbell again.
Okay, so this part now we look at radioactive emissions. Now, before we actually look at the radioactive emissions, you should know something about Marie Curie. Probably one of the most famous female scientists from in the past. She and her husband, Pierre, they were investigating uranium compounds. Now, unfortunately, they did not realize the dangers of these compounds. But what we know now is that they were really investigating very harmful radiation. All right. So they knew that what they were doing was, very interesting, but they did not know the dangers of it. However, their work is very important because they discovered 2 elements. One is polonium, and this is named after Poland, where Marie Curie is from, or was from. And the other one is radium. Now, both of these elements were found in ores of uranium, which has radioactive isotopes as well. Now, radium is found to be probably 1,000 times more radioactive than uranium. So as I said before, they were dealing with very dangerous and harmful radiation, but they did not know. And even now it is said that the books that she used are still radioactive. All right, so, all right, just a little bit on radium. Radium was once used to use in a particular paint to put on the dials of watches. And they had employed some females in factories to do that. Unfortunately for them, they also got radiation poisoning. All right. So these watches, they had the hands that glowed, natural glowing. All right. But that was due to the radiation. Nobody, or they did not know that it was harmful. And they painted themselves with the paint. And so they got radiation poisoning. Now, the Curies, apart from discovering the elements, they would have, determined some of the physical properties of these elements. And the Marie really worked on the radioactivity, all right? So due to their work, to show how important their work was, they were actually awarded the Nobel Prize for Physics, along with Henri Becquerel, who was the first to identify the radiation. All right, so they were working with him, but they did a lot of the work in discovering about the radiation. So they got a shared Nobel Prize in 1903. And then Marie Curie got another Nobel Prize for chemistry this time in 1911. So this shows how important the work that she did was. All right, and it's actually on your syllabus, so you need to know, describe Marie Curie's work in the field of radioactivity. All right, so it's something that you need to know. Now we look at the different types of radiation and how is it produced. Now, we mentioned that the nuclei of atoms can be unstable if they have too many neutrons or too little neutrons. All right. So in trying to become stable, the nuclei emit radiation, and they do so spontaneously, all right, in a random way. And this is called radioactivity. So radioactivity is the spontaneous emission of radiation by unstable atomic nuclei. All right, so they are trying to become stable. Just like anything that has too much energy, they release some of the energy to get to a lower energy state. All right. Now you have three ways in which this radiation comes, or three forms in which it comes, sorry. You have alpha radiation, beta radiation, and gamma radiation. Of course, these are Greek characters. All right. Now, alpha and beta are particles, and the alpha particles are actually nuclei of helium, element helium, just the bare nuclei, meaning 2 protons and 2 electrons that are bound together, no electrons. All right, just the nucleus of the helium atom, 2 protons, 2 neutrons. Due to this, if you recall, protons and neutrons have about the same approximate masses. So 2 and 2 is 4. We have a relative mass of 4 for the alpha particle, and a relative charge of +2 because of the 2 protons. All right, no electrons to cancel out these positive charges. So whenever you hear of alpha particles, you're thinking of helium nuclei. Beta particles are fast-moving electrons, and these are produced inside of the nucleus when a neutron decays. All right. Now, you have to be careful with this one because it says they are electrons, but you have to state that they are fast-moving electrons. They are not the regular electrons orbiting the nucleus. They are electrons that are formed inside of the nucleus and then ejected. All right. Now, since they are electrons, they'd have a relative charge of -1, but a mass of approximately 0. Their masses are negligible, so they are not considered to have any mass. All right. Now, gamma is electromagnetic radiation. We do not speak of gamma as particles, but as electromagnetic radiation. And these have very short wavelength. All right. And of course, radiation, rays have no mass nor charge. It's like pure energy. All right, so you need to know what are alpha particles, beta particles, and gamma rays. Further on, we'll need to know their behavior. Oh, this is Marie Curie in the lab. And we have just a brief look at polonium element, one of the elements that she discovered. Just for emphasis, not that you need to recall any information here, but if you see the periodic table, you will recognize that the symbol PO is for polonium. And then radium is Ra. So notice the atomic number 84 and 88. Very close to uranium. All right. Okay, now the range of the different particles. There is an apparatus or a device called a Geiger-Müller tube and a rate meter, which can measure the number of particles, right? That is the number of particles that the Geiger-Müller tube comes in contact with per second or per minute. The rate meter can show that. So if you want to find out the range of whether it's alpha, beta, or gamma radiation, you could have the tube placed in front of the radioactive source, and then you observe the reading on the rate meter, and then you move the tube further and further away from the source until there is a sudden drop in the reading of the rate meter. So by that, you would know at what distance from the source the radiation is negligible. So you know how far it can travel. For alpha particles, they cannot travel far. They just travel a few centimeters in air, probably about 10 centimeters maximum. Beta particles can travel further, more than 10 centimeters, while gamma rays can travel a few meters in air. So gamma rays have the greatest range, followed by beta particles, and then alpha particles have the smallest range. Now, if you reason it out, you'll understand why gamma rays have the greatest range. They are not particles, they are rays, they are radiation. And so they can pass through without much effect on themselves. They can pass through matter. However, alpha and beta particles, they will collide with other molecules, and that will stop them after some distance of traveling. All right. Because alpha particles are massive, they collide with more air particles. So they are stopped easily, or they are stopped shorter, while the beta particles are smaller. So they collide with less air particles. So they travel a slightly greater distance. All right, ionizing ability. When radiation comes in contact with other molecules, they can strip electrons from them. All right, this is called ionization. Sorry. So which of these have the greatest ionizing power? All right. Now, how you can detect this ionizing power is to use what is called a cloud chamber. All right. So in the cloud chamber, you would see different trails being produced by the different particles or different radiation. Alpha particles would produce thick, straight tracks. Beta particles produce bent, wispy tracks. Gamma rays, by themselves, they don't produce any tracks, but because of what they do to electrons, then electrons will produce some faint tracks. And then these tracks can be used to tell where the gamma rays would have passed, right? So these tracks are secondary tracks because they are not produced by the gamma rays themselves, but the electrons that the gamma rays affected. So these tracks would be faint, but alpha particles would produce very pronounced and straight tracks, while the beta particles would produce bent, wispy tracks. All right. So this is the cloud chamber. Actually, one type of cloud chamber. The details of it, I don't think you're to know the details, just that when radiation passes through it, you can see the trails that the radiation make. Just like if a car was to travel on a muddy road, you would see the tracks from the car tire, different from the tracks made by a bicycle, right? So that's basically like showing the footprint of the radiation. This is one of different types of cloud chamber. Then we have a diagram. It uses saturated alcohol vapor, for example, and solid carbon dioxide, same thing we call dry ice, so that the vapor is cooled. And when the radiation passes through, it will cause you to see the different patterns. So we'll show for the alpha particle, you will see these short straight tracks. They are thick, short. It shows that they don't travel far. Beta particles produce some bent tracks here, very fine. While for the gamma rays, you'll notice very faint tracks being produced. All right, so these are the tracks produced in the cloud chamber by the different types of radiation. This is how the apparatus could be set up to measure the range of the different types of radiation. You have the Geiger-Müller tube here, which is connected to the rate meter, and you have a source of radiation. So this can be moved to different distances, and the rate meter observed. All right. So you just need to know how to describe such an experiment, but not necessarily to draw an accurate diagram. Although you could, make up a diagram of your own. All right, the behavior of the different types of radiation in magnetic and electric fields. Now, both the magnetic and electric fields will have an effect on alpha and beta particles because they have a charge. However, gamma rays have no charge, and therefore they are not affected by the electric and magnetic fields. For the magnetic field, you can use Fleming's left-hand rule to predict the deflection of the alpha particles. And once you know the direction in which the alpha particles are deflected, the beta particles will be deflected in the opposite direction, but to a greater extent. All right, and this is due to their smaller masses. So they are more affected than the alpha particles. Alpha particles are much more massive than beta particles. So they will be affected less than the beta particles. Gamma rays are unaffected, so they pass straight through. Alpha particles are deflected in the direction of the electric field. Remember, the electric field direction is defined as the direction of the force on a positive charge if it is placed in the field. And alpha particles are positively charged, so they will be deflected in the same direction as the electric field, while beta particles are negatively charged, so they will be deflected in the opposite direction. Again, gamma rays are not troubled by the electric field. All right, so during a nuclear reaction, mass and charge are conserved. So the sum of the masses and the sum of the charges of the products is equal to that of the reactants. So when you look at a nuclear equation, you can find the total of the mass on one side, and it should be equal to the total on the other side. All right. Same thing with the charge. And you'll know more about this when we actually look at an equation. All right. How can you show that the decay process is random? The actual radioactive decay is a random process in that it is not known which atom will decay or when it will decay. But it is certain that after some time, some atoms will decay. So you can use something as simple as a dice throw, where a large number of dice are used and they are thrown on the ground. And then those that fall on a 6 are taken out after each throw, and then you repeat. So you count the number of dice remaining after each throw. And when you look at the pattern, you'll see that there is a decrease, a gradual decrease in the number that remains. And that decrease can be predicted to some extent. What you cannot predict, though, is which of the dice will fall on a 6. So this is the same way which atoms decay, radioactive atoms, all right? You don't know which one will decay or when it will decay, but you know that after some time, some of them will decay or half of them will decay, all right? Other thing is that the decay process is not dependent on anything outside of the nucleus. So it doesn't matter what is happening outside. You could hammer the atoms, you could put them in acid, you could heat them. Those things will not change how fast the atom decay. So the only thing that the decay process depends on is what is happening inside of the nucleus, not what is happening outside. All right, so we'll go now to a past paper question. It's January 2020. That's just last year. Question 6. Miss Rose.
All right, so we are told that there are 3 emissions, alpha, beta, and gamma from a radioactive source. They are subjected to a uniform magnetic field perpendicular to their path as shown in the figure. So here we have figure 5. So we have the radioactive source, the black oval in the middle there. That's the radioactive source, and it's emitting alpha particles, beta particles, and gamma radiation. Right? And the magnetic field is into the paper or the screen, whichever way you want to look at it. So we are asked to trace the path of the 3 emissions as they pass through the magnetic field. So we need to draw 3 rays to represent the path of the alpha, beta, and gamma radiation respectively. Right. So it was mentioned earlier that alpha particles and beta particles are affected by magnetic and electric fields because they have charges. However, gamma radiation will not be affected by either a magnetic field or an electric field. Now, to determine the path that the radiation will take, we can use Fleming's left-hand rule, which will basically, we will use our forefinger to indicate the direction of the magnetic field that is into the screen. Our middle finger would point in the direction of the conventional current. So remember that alpha particles are positively charged. So our radioactive source is right in that little box there. So basically the radiation would be emitting you could say upwards into the field generally. Now the alpha particles, you would point your middle finger upwards to show the direction of the conventional current. So if your forefinger is into the screen and your middle finger is pointing up, you would notice that your thumb points to the left. So it means therefore that the alpha particles would be deflected or they would deviate to the left. All right. Now, the beta particles are negatively charged, so they will be deflected in the opposite direction to the alpha particles. So they would be deflected to the right. Now notice that we have drawn the rays so that the alpha particle ray looks a little bit straighter than the beta particle. And that is because, remember we said that beta particles are very, very light. They're high speed electrons, so their mass is pretty much negligible. They will be deflected much more than the alpha particles, which are heavier. All right. So when you draw these rays, you need to ensure that the beta particle ray, it bends more than the alpha particle. Now, as we said earlier, gamma rays are not affected by magnetic fields, so they will pass straight through upwards. All right. So that would be for the magnetic field. Right. Now you're told that the magnetic field is replaced by an electric field shown in figure 6, and you're asked again to draw the three rays to represent the path of the alpha emission, the gamma emission, as they pass through the electric field. Now you notice that the positive charge is to the left and the negative charge is to the right, and the radioactive source is still being basically projecting upwards into that magnetic field, the electric field, sorry. So notice once again, we have to bear in mind the charges, the relative charges of the alpha particle and the beta particle. Once again, gamma radiation is unaffected by electric fields, so you would not expect it to be deflected. Now, alpha particles are, they have an overall positive charge. So if they are positively charged, then you would expect that they would be deviating towards the negative because opposite charges will attract. So the alpha particles will deviate towards the negative section of the electric field. Beta particles, which are negatively charged, will be deviated towards the positive section of the electric field. And once again, the beta particles will be deviated more than the alpha particles because they are lighter, much lighter than the alpha particles. And the gamma radiation will pass straight through the field undeviated because they are not affected by the electric field. Right? So it's important for you to know how to apply Fleming's left-hand rule and sign convention to determine the direction of the deviation beta particles in magnetic and electric fields. Now, part B of the same question says that there's an unstable isotope of lead 210 undergoes exactly two sequential beta particle decays followed by an alpha particle decay to become stable lead 206. Now, with reference to the information in table 3, you're asked to write the nuclear equations that will result in the formation of stable lead-206 from lead-210. You're also told that the atomic number of lead is 82. So you're first asked to write the first beta decay equation. Now remember that whenever there is radioactive decay, it follows the law of conservation of mass and charge. So we will start off with lead 210. Lead has the mass number of lead here is 210 and the atomic number is 82. So that's the bottom number. So when that isotope decays, it emits a beta particle, which is a high-speed electron. And we know that the electron has 0 mass and the charge is -1. Right? So based on this information, we know that we would start off with the species having an atomic number of 82, and we need to figure out which species would have a number that when you add -1 to it, you get 82, and that's 83. So that would mean that the element that we would write would be Bi, which is bismuth. So the atomic number there is 83, and the mass number would remain the same, which is 210. So notice if you add the numbers on the right, 210 plus 0, you would get 210 again. And you add 83 plus -1, you would get 82. Right? So you can use that kind of procedure to check or to double check your answer. Just ensure that when you add the numbers to the right, you get the same number that you would have on the left. All right. So that's the first beta decay equation. Now for the second beta decay equation, you would start off with the species, the daughter nuclide from the first beta equation, which would be the bismuth, 210, 83, and it would emit a beta particle, and you would also get another daughter nuclide, and that one would be polonium, which we will double check in our calculations to ensure that it's correct. So remember that once again, the beta particle has a mass of 0. The atomic number, or the charge, sorry, is -1. So in order to figure out what we need to put for polonium, we can use the law of conservation of mass and charge. So we know that the mass number would remain the same and the atomic number would be increased by 1. And of course, you can see that it will correlate with what's in the table. The atomic number of polonium is 84. So we know that we are on the right track. Right, so you can double check again. 210 plus 0 is 210. And then 84 plus -1 is 83. All right. Now for the alpha decay equation, we'll use the daughter nuclide, the polonium is now going to become parent nuclide. So we start off with polonium, and remember we said the end product is stable lead-206. So we start off with polonium, and that undergoes alpha decay to give stable lead-206. Now the alpha particle, as we said, is a helium nuclei, which means that it has a mass of 4 and a charge of +2. So we know that in order to get 210 from 4, we must add 206. So that would be our mass number. And the atomic number would be 84 minus 2, which is 82. Okay. So whenever you have beta decay, you represent the beta particle by using an E, which represents electron. You put 0 because the mass of the electron is 0 pretty much. And the charge is -1. So the atomic number there, you use -1. And for alpha decay, we use He, which is the symbol for helium, because alpha particles are helium nuclei. And we know there are 2 protons and 2 neutrons. So the mass is 4. And the charge is +2 because there are no electrons. All right. Right. I think we have another part. Part two. Right. We have a radioactive element. Oh, sorry. This question is from January 2017, and we're looking at question 6, part C. So we have a radioactive element X, which undergoes a decay process, which results in the formation of a new element Y, as shown in the equation. We have the equation there being presented. And notice that the daughter nuclide, we don't know the mass number nor the atomic number, but we know that a helium nucleus has been ejected from element X. So we are now asked to state the type of decay process that has occurred. And the big giveaway there, of course, is the helium nucleus. As we mentioned earlier, once you see the helium nucleus, you know that it's alpha decay because the alpha particle is analogous to the helium nucleus. All right. Secondly, we are asked to determine the values of P and Q. Now, as we said, in keeping with the laws of conservation of mass and charge, we need to ensure that whatever the mass numbers that we have on the product side are equal to the mass number of the reactant. And the same thing goes for the charge. So in order to determine the value of P, we notice that whatever P is plus 4 would give us 222. So to find what P is, we simply subtract 4 from 222, and that would give us 218. Similarly, to determine what Q is, we need to find out what number do we add to 2 to get 76. So Q is equal to the difference between 76 and 2. So therefore, to find the value of Q, we subtract 2 from 76, which gives us a value of 74. Mhm. Right. We are now asked to write the reaction equation if element Y, which is the element that we just found the mass and atomic numbers for, if that new element undergoes beta decay, forms a new element Z, we want to write the reaction equation. So of course, remember that in beta decay, there is a high speed electron that is ejected. So we can start off by having our reactant or the parent nuclide Y on the left, which decays to give Z plus that high speed electron. So we can then put in the values for P and Q that we just calculated, and then we can put in our 0 for the mass of the electron or the beta particle, and the charge is -1. So of course, in beta decay, the mass of the particle remains unchanged. All right, so we would have 218 for the mass number, and the atomic number will increase by 1. So we have 74. So that means on the daughter nuclide, we will have 75. Right? And of course, you can always say, all right, 75 plus -1 is equal to 74. 218 plus 0 is equal to 218. So we can use that to double check. So finally, we are asked to describe or how radioactive decay affects a particle's mass. All right. Now, I assume that the question is asking about the mass of the particle that has undergone decay. We know that during alpha decay, the mass decreases by 4 units because 2 protons and 2 neutrons have been ejected, whereas during beta decay, the mass remains unchanged. In gamma decay as well, because gamma radiation is just the release of energy, there is no change in the mass with gamma decay either. Right? Now, usually when gamma decay occurs, it tends to be in tandem with either alpha or beta decay. But if gamma decay occurs by itself, then there is no change in the mass, nor any change in the charge. There is just a release of energy. Right? We have a question from all the way back in May, June of 1990. And it simply asks us to state the composition of an alpha particle. Mr. Campbell mentioned it quite a few times, as have I. An alpha particle consists of 2 protons and 2 neutrons tightly bound together. And you can also mention that it is analogous to a helium nucleus. Okay. So we have another question from 2015 paper from May and June, and we are looking at question 1, part D. You're asked to state 2 types of radioactive emissions. Now note there are 3, so you can state any 2. You can either state for alpha particles or beta particles or gamma radiation or any combination of 2 of those 3. Which type of radioactive emission is the most dangerous to human tissue? And that is gamma radiation, due to its high energy and its high penetrating power. Of course, we know that it can penetrate human flesh quite easily, and it can cause cancer and radiation poisoning, which is, as Mr. Campbell alluded to, what ultimately caused the demise of Marie Curie, because of course she and her husband did not realize the dangers of radiation, specifically gamma radiation. So we are moving on to half-life now. I'll hand over to Mr. Campbell 1 second.
Okay, so last topic, half-life. All right, so what you should know about half-life is that the half-life of an element is the time it takes for half of the original number of the radioactive nuclei to decay, or if you want to use mass or activity. So you could replace number with mass or activity. Any way you define it, once you talk about the time taken for half of that particular property to decrease to half its value, right? Then you'll be talking about the half-life. Now, the activity is the rate at which the atoms are decaying or disintegrating. This is measured in becquerels. Mentioned Henri Becquerel before. 1 becquerel is 1 disintegration per second. All right, now the same fraction of radioactive atom decays in equal intervals of time. So every half-life, you're going to get a certain number of particles decaying, certain number of nuclei decaying. You're going to have a certain mass decaying, right? Same amount each time, or the same fraction will decay each time. Now, what this causes is an exponential decrease in whatever property you're looking at. So if you're looking at the number of nuclei, then the number will decrease exponentially. If you're looking at the mass will decrease exponentially. Or if you're looking at the activity, that will decrease exponentially. So if we plot a graph of probably the number of particles against the time, then we'll get an exponential, a graph which shows exponential decrease, sorry. So if we started out with 100 particles and the half-life is, let's say, well, this says 5.27 years. Then, well, this is not showing the exact half-life, but if we check the time for the number to decrease to half its original value, we start at 100, how long it takes to go to 50, this would be 1. And then from 50 to 25, it's another 1 in terms of the scale here. All right. So once we check the time that it takes for the number to decrease to half of the original value, then we will have a value for the half-life. Otherwise, if we are looking at the mass, so if we have 10 grams of the original substance, then after 1 half-life, you will only have 5 grams of that same substance, because 5 grams would have disintegrated into something else. All right. So it's not that we are saying the matter is destroyed, but then the type of atoms that you have will be different. So starting out with 10 grams of, let's say, cobalt 60, whenever one half-life passes, you will only have 5 grams of that cobalt-60. The other 5 grams would have been converted into something else. Okay, so we can look at this table here, which shows the fraction of the substance remaining after 5 half-lives each time. So we have half remaining after 1 half-life, a quarter remaining after 2 half-lives, which is 1/2 to the second power. After 3 half-lives, we have 1/8, or 1/2 to the third, and so on. So we can use this fraction or these fractions to find out how many half-lives have passed. All right, so we have a question here from May, June 2017. This is also from paper 3. Paper 3 is a practical paper which you wouldn't do, but the questions are very much questions that can come on any paper. So we'll go ahead with Miss Rose.
All right. All right. So we are told that students carrying out an experiment to demonstrate a random process such as radioactive decay used a large number of dice to represent atoms. The dice were tossed repeatedly, with those showing 6 being discarded after each throw. Now the results are going to be shown in table 1, which is on the next slide. All right. So notice there are 14 throws that were made. There is a column for dice discarded and a column for the number of dice remaining. So you're asked to complete the table by inserting the number of dice discarded for 4 throws, 4 to 13. Now notice that if you look at the first 4 rows, you could see the trend is that to get the number of dice discarded, you subtract the number of dice remaining after the second from the number of dice remaining from after the first throw. So we would subtract 68 from 80, that gives us 12. For the third row, you would subtract 57 from 68, that gives 11, and so on. So we would use that same procedure to work out the dice discarded for throws 4 to 13. So we would subtract 44 from 51, that gives us 7. Then we can subtract 38 from 44, that will give us 6. And then subtract 31 from 38, that's equal to 7. We then subtract 25 from 31, which is 6. 21 from 25, which is 4. 16 from 21, which is 5. 15 from 16, which is 1. 12 from 15, which is 3. 12 from 10, which is 2. 8 from 10, which is 2. And then for throw number 14, it would be 6 from 8, which is 2. Right, so that's 2 marks there. Right. So the next question says to use the data in table 1 to plot a graph of the dice remaining versus the throw. So the number of dice remaining would be on the y-axis and the throw would be on the x-axis. So we have that graph prepared. You notice that once all the points are plotted, that the trend is one of an exponential decay, right? So notice that you would get a smooth curve, which shows that the number of dice remaining decreases exponentially, all right? And this is basically how radioactive decay works. All right? Of course, we label our axes as normal, and we ensure that we draw our points neatly, and we try as best as possible to draw a smooth curve using our freehand. Right. Now the next part of the question speaks to half-life, and notice that we will come back to the graph, and all right, so we're asked to use the graph to determine an average value for the half-life of the process. So what you would do is we can go back to the graph and notice that we start off with the number of dice remaining at 80. So we could find out how many throws it takes for the number of dice to become 40. And you would just show that, read off the value from the graph, and we can see that that would be equal to 4.6. So the 4.6 there would represent one half-life. But remember, we need to find average half-life. So we need to do this more than once. So you can also find out how many throws it would take to get the number of dice remaining from 40 to 20, because 20 is half of 40. All right, so the number of throws where the dice is 40 is 4.6, and at 20 dice remaining, the number of throws is 8.2. So in order to deduce the half-life from that, we would need to subtract the 4.6 from 8.2 in order to get another value for the half-life. So of course, 8.2 minus 4.6 would give us one other value for half-life. Of course, you can do this any number of times. So you can do it 3 or 4 times and find the average. Use the same formula that you would be accustomed to finding average. So you take the two half-lives that you have 4.6 and 3, you add them and divide by the number of throws, which would give us a value of 4.1 for the average. So of course, if you did this, like you could also take the number of throws from say 70 dice to 35 dice. That would be one half-life as well. You could do from 60 to 30, etc. So it doesn't necessarily have to be 80 to 40 and then 40 to 20. As long as you find two values on the graph where the first value is twice the amount of the second, then that would be equivalent to one half-life as well. Right? So sometimes they'll tell you to use 2 or 3 values, or they might tell you to use 4. So you can use your discretion, but just ensure that you show the values or you show the read off on the graph and you find the average half-life. So if you use 4, you would add the 4 readings and divide by 4. If you used 3, you would add the 3 half-lives and divide by 3. So in this case, we did 2. So we have the first half-life being 4.6, the second is 3.6. So we add those two values and divide by 2 to get an average half-life of 4.1 throws. So in other words, every 4.1 throws, then the number of dice remaining would decrease by half. Right? So this is another question. This is from the 2008 May-June paper. We're looking at questions 3D to E. It asks how many half-lives it would take for a sample of carbon-14 to be reduced to 1 over 32 of its original mass. Now remember, we just mentioned earlier that for every half-life, the amount decreases by half. So you can approach it in a number of ways. You can use a formula, or you can use a table similar to what we had earlier. So at 0 half-lives, then all of the mass would be there, or the original mass would be there. After 1 half-life, then the mass is going to be reduced to half. So the fraction remaining would be a half. After 2 half-lives, the fraction remaining would be a half of a half, which is a quarter. After 3 half-lives, then you'd have a half of a quarter, which is 1/8. After 4 half-lives, you'd have a half of 1/8, which is 1/16. So to get a fraction of 1 over 32, 5 half-lives would need to have passed. So you can approach it in this way. Another way that you can look at it is to remember that the fraction remaining is basically going to be equal to 1 divided by 2 to the power of n, where n represents the number of half-lives. So if the fraction remaining is 1 over 32, we need to find out what 1 over 32 is equal to in terms of base 10. So 2 to the 5th power is 32. So 1 over 2 to the 5th power would be equal to 1 over 32. Right? So that's one other way that you can approach it. Right. The next part of the question says, given that carbon-14 has a half-life of 5,700 years, determine how long it would take for this reduction to occur. Now you will note that we just determined that 5 half-lives would have taken place. So if 5 half-lives take place, then we just need to multiply the 5 by 5,700 to determine how long that would be. So remember, 1 half-life is 5,700 years. So 5 half-lives would be equal to 5 times 5,700. And that's equal to 28,500 years. All right. So another question. This is from the May-June 2011 paper, question 6B, part 1. Now, a gram of living plant material with carbon-14 decays at a rate of about 16 disintegrations per minute, and that's the activity. When the plant dies, the carbon-14 decays with a half-life of 5,600 years. Now, 1 gram of the dead plant is found to disintegrate at about 1 disintegration per minute, and you're asked to calculate the probable age of the plant. Now, remember that when plants are living, right, they will absorb carbon dioxide and they will also emit carbon. So while the plant is alive, the amount of carbon that is present will basically be pretty much constant. Now, once the plant dies, there is no more absorption of carbon dioxide. So the carbon that is present is going to decay over time. So based on the information from the question, we can say that the activity of the plant is going to decrease by half every 5,600 years, right? So the fraction that is remaining would be 1 over 16 or 1/16, because remember it was initially at 60 disintegrations per minute, but now it is 1 disintegration per minute. All right, so the fraction remains is 1 over 16, which means that the number of half-lives remaining would, or the number of half-lives that would have passed would be 4, because 16 is 2 to the power of 4. All right. So if we know that 4 half-lives have passed, then we can determine the age of the plant by multiplying the half-life by the number of half-lives which have taken place. So it's 4 half-lives, and we multiply that by 5,600, and that's 22,400 years. Okay. So we are going to go through one more question, and then we'll take any questions you may have afterwards. Now, this question is from 1990, question 36C. We're told that the activity of a sample of a radioactive element decreases to a quarter of its original value in 1 hour. And you're asked to calculate the half-life of the sample. Of course, you can look at this in a number of ways. You can determine how many half-lives have passed based on the fraction that remains. So remember that the fraction that is remaining is a quarter. So if a quarter is remaining, then it means that 2 half-lives would have passed, because a quarter is the same as 1 over 2 to the second power. So n is equal to 2, and 2 would the n represents the number of half-lives. So if 2 half-lives have passed and it takes 1 hour for 2 half-lives to pass, then it means that we can calculate the half-life knowing the time that has passed and the half-life, the number of half-lives. So we can use the equation that the half-life is equal to the time elapsed divided by the number of half-lives. So that would be 1 hour divided by 2, and that gives us 0.5 hour, which is the same as 30 minutes. You can also look at it from the standpoint that if we know that 2 half-lives have passed, then it means that 1 half-life would have taken place in 30 minutes, and the second half-life would have taken place in the other 30 minutes. So you could determine that the half-life would be 30 minutes based on that as well. Right. So finally, we're looking at the activity of a radioactive sample measured over a 24-day period, and the results are recorded in the table shown. This question is from the May-June 2015 paper, the data analysis question. So we have the results of the activity of a radioactive sample over a 24-day period. The table is not coming up at all. going to All right, so give me one moment. Let me switch my screen. All right, so so here we have our table. The time was divided, and we have the activity in disintegrations per second. So we start off with the initial activity at 40 disintegrations per second, and it decreases so that at the end of the 24-day period, the activity is 5 disintegrations per second. Okay. The first question asks us to plot a graph of the activity versus the time. The activity would be on the y-axis and the time on the x-axis. So we have our title, graph showing the activity against time for a radioactive sample over a 24-day period. And our axes are labeled activity on the y-axis and the time on the x-axis. So it says to use your graph to calculate the average half-life of the sample, and you're supposed to determine from the average of 2 or 3 values. All right? So notice that from the graph, starting off an activity of 40 disintegrations per second, the time at which the activity is 40 is 0, and then half of 40 is 20. The time at which it takes to get to 20 disintegrations per second is 8 days. So that would be 1 half-life. You could also take the time at which the activity is 16 disintegrations per second and the time at which the activity is 8 disintegrations per second. So we would subtract the 18 and this would be 10.2, right? So we would have our 2 half-life values there and we can calculate the average, right? So have the information here at 40 disintegrations per second, the time is 0. At 20 disintegrations per second, the time is 8 days. So the half-life there is 8 days. At 16 disintegrations per second, the time is 10.4 days. And at 8 disintegrations per second, the time is 18 days, which means the half-life is 7.6 days. And then we can find the average half-life by adding 8 days plus 7.6 days and then dividing by 2. And that would give us an average half-life of 7.8 days, which we can round up to 8 days. So this should be 8 plus 7.6 divided by 2 as its average. All right. So of course you could use another value to obtain the half-life, and then you would add that to the 2 that you have and divide by 3. But of course it says you can use 2, so 2 is fine as well. You're asked to then use the graph to determine the activity of the sample after 25 days. Now remember that the graph, the values stop at 24 days, which is why we always advise students to try as best as possible to extend the graph so that you can extrapolate if necessary. So we need to find 25 days on our graph and read off the corresponding y value, and that would give us the activity for 25 days. Okay? So the graph is not so very clear, but 25 days would be somewhere right off somewhere off here. So you'd read off the corresponding Y value, and that would give you the activity after 25 days, sorry. So from the graph, it's 4.6 disintegrations per second. You show your readoff value on the graph and you write the answer on the paper, and that's your 2 marks. So that's it for that question. Pretty much it for the end of the session. I'll hand over back to Mr. Campbell and we can take any questions if you have any.
All right, just taking questions now. If persons have any questions. All right, one person saying no questions. Does that go for everybody else? All right, so I guess that's it then. Just want to thank everybody for coming. And I know that this should be a very helpful session for you guys. All the best in your exams. And remember to like and share, subscribe to our channel if you haven't done so as yet. There are multiple choice workout past papers on this channel. All right, so when you're ready for your multiple choice workout, you can go here. So all the best, guys.
All the best, everyone.
All right, you're welcome.